Back to chapter 2. Today we're going to be talking about the chemistry of life, or the chemical organization of life. Remember, we had those different levels of organization. This is that most basic level, the atomic molecular levels. In this set of videos for chapter 2, we're going to be talking about elements, defining them, defining what atoms are, and how they're structured. Later on, we're going to be also looking at electron shells, and in particular, what that means in terms of what are called the big four elements. These big four elements constitute 96% of your overall body chemistry. So those are obviously four very important ones, and it turns out they're so important because of the way the electrons are structured. So we'll be looking at that. The next major topic is how bonds are formed. There are three major bonds in the biology of a human body, so we'll be discussing those. Role of water. How does it work? Well, it obviously is a really great solvent, so it's going to dissolve many things in our body. And because of that, we have to look at what's called the pH, because we're going to see that there is a potential for an upset of your homeostasis. So go back and look at that if you don't remember the definition. The upset of your homeostasis if there are too many hydrogen ions or too few hydrogen ions within your bodily fluids. Next, we'll be looking and defining energy. We'll talk about the different types of reactions that are going to occur in the human body, and also how they result in a series of reactions dealing with polymerization. Polymerization results in these massive molecules called macromolecules. There are four types of those. And macromolecules are carbon-based molecules that we call organic molecules. So we'll be defining all of that as well. Okay, so those are what we'll be covering in this set of videos. Not all in this single one, but in this set of videos. And let's just start by defining what matter is. Matter is our most basic definition. So matter is anything that has volume, in other words, it takes up space, and as a consequence also must have mass. So those are the two requirements to call a particular item matter. Okay, and the most basic forms of matter that we're going to consider in this class are elements. So elements are the most basic forms of matter that cannot be easily degraded. There are 92 naturally occurring elements, and of these 92, 26 are essential for us to be existing today, for us to be alive. And I'm sure you've seen at some point the periodic table, and you'll see all these elements arranged here in various numbers. You'll see a lot higher numbers than 92. Don't get worried about that. Those are man-made elements. There are only 92 naturally occurring elements. And so of these, we talked about 26 being incredibly important, certainly hydrogen, lithium, carbon, nitrogen, oxygen. I mean, there's a whole series of them. Sodium, magnesium, potassium, calcium, phosphorus, sulfur. I mean, there's tons of them here in the early high numbers. We'll also be dealing with, especially in AP2, iron, which is number 26, iodine, number 53, and a few others scattered about the periodic table. Now also I want you to note here that associated with the letters representing each of the elements, you'll get used to those. It's kind of like the body parts. You'll get used to the letters that represent each of the elements. Above them is a single integer. We'll be discussing that. It's called the atomic number. And below the letter is the atomic mass. Generally in this, at least in this periodic table, it's a decimal number. For hydrogen, 1.0079. Why is that? We'll talk about that. All right, so the structure of an atom. An atom has a particular structure, and this is true of all atoms that fit whatever element they are a part of. So we can represent atoms through one of two models. Regardless of which model we use, both of them exhibit a central nucleus. And the central nucleus of an atom contains a positively charged proton, or more than just one, and zero charge neutrons. So a nucleus contains the positively charged protons and zero charged neutrons. And in Model A, they're surrounded by a cloud of electrons. Now that's kind of hard for us to abstract to and put meaning to, so generally the way it'll be represented in A&P is with the shell model. And as we'll note with the shells have electrons at specific positions, and these represent energy levels. We'll talk a little bit more about that in a couple slides. Now, up in the upper right corner, you see a beautiful representation, not a representation, excuse me, this is a photograph, actual photographs of atom. This is amazing. Now, how do atoms correspond to specific elements? Well, think of the periodic table as a series of bins in a grocery store, right? So we have to put things in the bins that are common, right? So you're going to put pinto beans in one bin and lima beans in another. And so because of their characteristics, right, that when they have different characteristics, you put them in a common bin. Now, it's the same thing here. When we have atoms with similar characteristics, we're going to put them in the common bin. Say, for carbon, we're going to put atoms that have 6 protons and 6 neutrons in their nucleus and 6 electrons in their electron shells. We'll put them in the carbon bin. For the hydrogen bin, we'll put 1 proton and 1 electron. Atoms that have 1 proton, 1 electron, we'll put them in the hydrogen bin. And so for the helium bin, we'll have 2 protons, 2 neutrons, and 2 electrons for our atom. We'll dump all those in the helium. So atoms will get deposited into the bins in which they show those particular characteristics. Now, as we continue on, let's look at shell models for several different atoms that are of particular importance to A&P. And what we're going to note with these electron models is they're different, right? So certainly we're interested in the nucleus. And remember I talked to you about that integer number that was above the letter for the element. So if we're talking about H, we had a 1 above it. That means its atomic number is 1. And the atomic number represents the number of protons in the nucleus. Now the number below it was its atomic mass. And the atomic mass is the number of protons plus the number of neutrons. We will, for hydrogen, it would be the same number. The number of protons is 1. The number of protons plus neutrons is 1 because hydrogen is the simplest element and it has no neutrons in its nucleus. Another thing you need to realize about atoms is that the number of protons must always equal the number of electrons. So they should always equal out and the charge will always be 0. So let's start looking at those definitions and start looking at what that means here in terms of these different elements. Let's start with carbon. And carbon has, on the left-hand side, has 6 protons, 6 electrons, and 6 neutrons. That means its atomic number is 6, but its atomic mass is 12 because we add the number of neutrons plus the number of protons. Moving up to nitrogens, we see it has 7 protons, 7 neutrons, and 7 electrons. Its atomic number is 7, its atomic mass is 14. Notice for both it and nitrogen, number of protons, it and carbon, excuse me, the number of protons equals the number of electrons. Moving on up, we start to see sodium. Sodium has 11 protons in its nuclear core, 12 neutrons, so it doesn't always equal in terms of protons and neutrons, so put that out of your mind if you were thinking that. But we know the number of protons is equal to the number of electrons, so it has 11 electrons as well. Atomic number 11, atomic mass 23. A much larger element, or atom, that fits the elemental description of potassium has 19 protons, 20 neutrons, and 19 electrons. So its atomic number is 19, and its atomic mass is 39. There are a few more things we need to note in this figure. Note that when you take atomic mass and subtract the atomic number from that, you get the number of neutrons. So we can tell everything about an element given the atomic mass and the atomic number, right? So take the atomic number, you know that's the number of protons, then that equals the number of electrons. So you get both those out of the way. Then take the atomic mass, subtract the atomic number, you get the number of neutrons. So we know everything we need to about that element at this point. Now what this really doesn't tell you is how these atoms are going to interact with each other. That doesn't depend on the nucleus. It depends on how the electrons are arranged. And you can see for each of these four displayed here, each of these four atoms, that they're different electron arrangements. First, what's common among all of them is you'll note the innermost shell, the circle, the orbit closest to the nucleus is going to be only 2 electrons. We'll never have more than that. There's only one element where there can only be 1 electron in this innermost shell, and that's hydrogen, right? Because it only has 1 proton, and you know the number of protons equals the number of electrons. Okay, so only 2 can ever be in the first innermost shell, the one closest to the nucleus. The second shell, the next one out, can have up to 8 electrons. And so we can see that represented in the carbon atom. It has only 6 total electrons. We know there are 2 in the innermost shell. That leaves 4 electrons to be in the second shell. But it can have up to 8. So if we move up to nitrogen, which has 1 more electron, it's going to have 5 electrons in its outer shell, or second shell. We move up to sodium, it has 2 in the innermost. It has 8, that fills up the second shell, and the third shell then has that extra electron, that 11th electron. Now this third shell can have up to 8, as far as we're concerned in the biochemistry aspect of ANP. So the third shell can have up to 8, and we see in potassium this is put to use really quickly. We have 2 in the innermost, next to the nucleus, 8 in the second, 8 in the third, and we begin our fourth shell. So that's 8 plus 8 plus 2, that's 18 total electrons. We know potassium has 19, thus it has an outermost electron, 1 sitting in that outer shell. What do these shells represent? Well, this is showing you it represents energy. And the electrons that are closest to the nucleus have the least energy. And if I can get one take-home message here, it's that energy equals instability. The greater the energy content, the more unstable an atom is. So if you have 2 electrons, they are very stable because they are near the nuclear core. Protons are positively charged, electrons are negatively charged. And so they attract each other. There's a very stable bonding there. But moving out to the second shell, we're going to have a higher energy among those electrons because they're further away from the positive charges of the protons. And you get out to this, in the last example of potassium, you get out to that fourth shell where they have that single electron. It's incredibly energetic and so is very unstable. All right, enough on that big chart, but there was a lot there, right? Okay, so now we talk about the big four. The big four are these elements. Why are they the big four? Well, we'll talk about that. Hydrogen, oxygen, nitrogen, carbon. These are the 4 that make up 96% of your body. Hydrogen, why are these the big 4? Well, for hydrogen, it has 1 electron in its shell, right? It has 1 shell and it has 1 electron in that. But remember I said there could be 2 here. So it has an opening, if you will. It has a hole. And these holes that exist in these outer shells are called valences. All right? The electron that exists in the outer shell is called a valence electron. This is very important terminology. So hydrogen has a valence electron number of 1 and a valence number of 1. All right, we move up to oxygen. Oxygen has an atomic number of 8, so it has 2 electrons in its innermost shell, as usual, and has 6 electrons in its outermost shell. This means its valence electron number is 6, but its valence number is 2. This is because it has 2 holes. We're going to see that atoms want to have those holes filled. They want to have a full outer shell, in other words. So they want to have 8 electrons there. They want more electrons to get attached here to get a full outer shell. How's that going to happen? We're going to form bonds. More on that the next video, though. Nitrogen has an atomic number of 7, so it has 2 electrons in the innermost shell and 5 electrons in the outermost shell. And so has 3 holes, valence number of 3, valence electron number is 5. Okay? And finally, the big kahuna, the one that forms the basis for organic compounds, is carbon. It has, its atomic number is 6, and so it has 2 electrons in its innermost shell, 4 electrons in its outermost shell. And so this is kind of nice because its valence electron number is 4 and its valence number